Babylonian mathematics has been in the news lately. What it is it's these ancient clay tablets that they're finding in the vicinity of Ur-Kasdiz. Literally the city of Ur means light, of the Chaldeans, going back to the time of Hammurabi, mentioned in the Chumash, the variant of his name, Amar Pol, known as Nimrod. Now these are the days of Abraham, our patriarch, Avraham Avinu. And the fundamentalist Christians go so far as to say that Abraham was a giant among mathematicians and astronomers, that he used this to prove that there is a God or make a very strong case, so they basically threw him out and blotted out his name, but it survives in places like Josephus. In any event, what they're finding out is that the mathematics that they used are at times more advanced than what we're doing right now. They're simpler to use in their precise. They give you round numbers as an answer, as opposed to non-repeating decimals, like you get when you use the number pi, the ratio of a radius to the circumference of a circle, or calculus, which makes use of limits, or trigonometry, which makes use of, basically it's a calculation. They never come out on, they've rarely come out right on the button. What the Babylonians used was a base 60 system, like we use for our timekeeping today. That's its basis. We're also measurement of a circle where you have hours or degrees, minutes, and seconds, where it's 60 seconds equals 1 minute, 60 minutes equals 1 degree or 1 hour. The advantage is it's divisible evenly by 3, and also by 5, and also by 2 and 4 and 6 and really 8, kind of. You just get even numbers. That's its power. In the case of the use of what they call Pythagorean triplets, it gives you a precise number rather than an estimate of a sign. Now, what is a Pythagorean triplet? If you go back to your high school geometry and algebra, it's a right triangle where we know that the square of the hypotenuse, or the diagonal, equals the square of the other two sides. In other words, 3 squared, 9, plus 4 squared, 16, equals 25, which is 5 squared. It comes out nicely. Now, the one that I'm working on, and it's become a popular one on the internet, that is, they say that any product can be expressed as the differences between two squares. Now, a product might be 2 times 8 or 4 times 4. It becomes a rectangle. The Babylonians loved rectangles and squares, and by using the diagonal, you get a right triangle. So what they said was that any product of 2 numbers can be expressed as the difference between squares. Now, what is the difference between squares? As you have right here, you have a square that is 25, 5 times 5 is 25, okay, minus a square of 4 times 4, this one, that's 16, okay, equals a square of 9, right here, okay? So what I have done is you show 25, okay, the big square, minus 16, the middle square, equals 9, the small square. Now, that's one way you can express it. Now, what I've shown also is, what if you were going to do 25 minus 9? So you have two squares. I made the big one, and then which is 5 by 5. And then I blacked out 9 squares, a square in the middle. And you could say that this kind of a whole donut, the donut is the difference between two squares. Another way you can do it is you could put the square that you're subtracting, the black one, in the corner of the big square, and you wind up with an L shape. Now that L shape is going to be important. So let's continue. Now, what we have here, and I've chosen an unpleasant series of numbers, it's 9 times 13, which equals 117, and we're going to set this up as the difference between two squares. Now, the first thing that is done is you have a square that's 9 by 13 right here, okay? And what they did to set up this proof, or this technique, they used algorithms and not formulas, is they took the short side and they made a square of it in the rectangle. So you have this square, 9 by 9 by 9 and 9. Okay? And what you have also remaining of this 9 by 13 square is this is the remainder, which is 13 minus 9, or 4. And if you're going to be mathematical about it, what you have is A, which is the long side, minus B. Okay? That's this side here, which is going to be 9 by 4. Now, I put some dotted lines here because what we're going to do is cut that in half. Now, what the trick was is they were going to cut this part in half and move 1/2 of it to the top. Now, if you'll notice, when you made this square here, the top, the bottom too, but mainly the top, which is of interest, becomes the same size as this. So if you roll this on its side and put it on top, it'll fit nicely. Okay? So you wind up, as I said, with two squares. This one that was 4 by 9 becomes two squares that were 2 by 9. It's cut in half. 1/2 the long side versus the short, minus the short side, or 1/2 AB. And when we move it to the top, okay, all sorts of nice things happen. What we wind up with is we have this 9 by 9 square, but we also have a 9 plus 2 side, and we also have a 9 plus 2 bottom, 11, and we also have a 9 plus 2 on the top, and the 9 plus 2 on the other side adds up to 11. But the key thing is we have a square here that's 11 by 11. And if the two sides that were cut in half, their short side nomenclature is nice, okay, is both 2. Here it's 2. This is 2. This 2 is the same as this. This is the same as this. Because this is the same as this. This is just turned on its side. It was the larger rectangle cut in half. And what we have now is our L shape. Okay? It's not as exaggerated as before, but you have this part here, and there is the little square. And if you want to calculate the difference between squares, okay, you have one, the big square, that's 11 by 11, which is 121. And you have the smaller square, which is 2 by 2 or 4, and that adds up to the 117 that we were looking for. Specifically, the 13 times 9 was 117. So what we started was with two really clumsy numbers, and they kind of factored into nice numbers that we can work with. So I purposely chose to do this again with numbers that start out nice but then get a bit clumsy. And I put it all on one piece of paper. What I did was 3 times 10. Now that's going to be 30. And what you have here is 3 times 10. That's your original rectangle. Now, what I then did was I made the smaller side into a square, which is now going to be 3 by 3. And now we got a large excess rather than a small one. Okay, and we're going to get a nicer kind of L in this one. And the long side minus the short side, that's going to be 10 minus 3 is 7. Okay, so this is our 3 by 7 remainder. And if you cut that in half, remember, this is 3 squared. Okay, what we're going to wind up is one with a square that's 3 by 3.5. And if we take, this is the one we're going to move. We cut it in half at the red line, and we're going to turn it on its side. The 3 here is going to go here. And you're going to get a 3 by 3.5 rectangle. You also have a 3 by 3.5 rectangle here. Okay? And you've got the common side is the 3 by 3 one, and you're also going to have another side that's 3.5 by 3.5. And the total size of this whole square, we're going to take out the corner, is going to be 6.5. And the smaller square is 3.5 by 3.5. So let's take a look at it. 6.5 5 squared is going to be 42.25. Okay? And 3.5 is going to be 12.25. Now remember, we're taking out the 6 and a, this is the 6.5 square, and we're going to subtract from it the 3.5 square. We're looking for 30. We're saying the difference between these two squares is going to be 30. So 42.25, the big square, minus 12.25, the small square, equals 30, and it checks out. Thank you.